Now let's take a look at a different type of system that oscillates with simple harmonic motion, and we're talking about the physical pendulum. So for a physical pendulum, I want you to imagine, well, we can just sort of take any random shape. I don't know what you'd describe this as. Any case, if you cut a hole through it, pass a wire through that hole, and then allow it to come to rest, it'll always come to rest so that the center of mass lies directly below that pivot point. So the question goes, what if I take this object and now I pull it back? See if I can draw this all right. Yeah, I think you get the idea. So what if I were to pull it back some angle theta and let it go? Then this object is going to go swinging back and forth and behave very much like the mass on the spring, in that it's going to have maximum kinetic energy at the midpoint and maximum gravitational potential energy at the endpoints. So this would be the same thing if we took a metal rod. Take a bar of metal, drill a hole, maybe right there, and pull it back and let it swing, starting from this initial position. The center of mass is at the geometric center if it's a uniform rod, and the object has been displaced an angle of theta naught to start with. So let's apply Newton's laws. I'm going to ask you to recall some information from a few units back in our study of rotation of rigid bodies. So we know Newton's second law for translation says net force equals ma. There's an equivalent for rotation that says net torque equals I alpha. So what is the net torque on this system? Well, when it returns to the equilibrium position where it hangs vertically, there's a lever arm from the axis of rotation to the point where we treat gravity. We say that gravity is a force that acts as if it's exclusively pulling at the center of mass. And so in this case, when it's in orientation number 1, the point where you release it, and then moves to orientation number 2 when it goes to vertical. In orientation number 1, there is a torque because there's an angle between the lever arm and the force. However, in position number 2, the force and the lever arm align with each other, and so the torque equals 0 at that point. So if we picture it as the swinging rod at some point in between, then at that point there's a net torque, and it's equal to the cross product of the lever arm with the force. Now you might be tempted here to say the lever arm is L over 2. However, the hole that we pass the wire through to act as an axis isn't at the very end point, right? The hole is here, and so sure, the distance from the end point to the center of mass is L over 2, but this distance I don't know. So the best I could do is just call it some value r. And by the way, you might say you know the value of I, it's 1/12 ml squared. Well, that's only if it's rotated about an axis passing through its center. So, oh yeah, it's not 1/12, it's 1/3 ml squared. No, that's only if the axis passes through its very end point. So we could use the parallel axis theorem here, but that would require us to know what this value of r is. So best I can do is just leave this as I. So I want to keep this as generic as possible. In fact, I probably would keep the diagram like this, except it's a little harder to relate to. So imagining a rod with an axis through some unknown point represents a physical pendulum that's general enough that the equations we derive here can be applied to any shape physical pendulum, meaning we could take something like a baseball bat, drill a hole through it here, pull it back some angle and let it swing, and it'll behave with a simple harmonic motion, and the equations we're about to set forth and derive will govern the motion of this bat just as well as they would this uniform rod, just as well as they would this random sort of shape. So we're starting step one with this expression for torque, and we can make a substitution based on Newton's second law, replace net torque with I alpha. So I alpha is equal to R cross F. Well, F is mg, okay? So we get I alpha is equal to mgr sine. Anytime we take a cross product, then the magnitude of that cross product is just the magnitude of the two vectors multiplied by the sine of the angle between them. I should draw this a little more carefully. There's our axis of rotation. There's the lever arm R. And there's the force mg. And it's pulled back some angle of theta. So the angle between them you might think is, oh, it's this large angle. But then again, I could just extend the line of the lever arm, and so this angle is the exact same theta. Yeah, so sure, this is just sine of theta. Actually, I think this deserves a negative sign, correct? In other words, if I release it from rest and it's going to accelerate in this direction, if the value of the angular acceleration is clockwise, the cross product of R and mg is a counterclockwise. The torque then is clockwise as well, but the angular displacement, theta, we'd imagine pulling it back in the counterclockwise direction. So in other words, when theta is negative, the torque and alpha are both positive. So this is kind of like when we write Hooke's law. We don't say F equals kx, we say F equals negative kx due to the nature of the restoring force. So because this is a restoring torque, we have to have the negative sign here. Okay, moving on to step 4. Hopefully this starts to look familiar. We're going to go through a similar process as we did for the object falling through the center of the earth and for the mass on a spring. We're going to see what Newton's law suggests about the second derivative of position with respect to time. Here we're not talking about position in meters, we're talking about position in radians, or the angular position. In any case, what does Newton's second law suggest about the second derivative of position with respect to time? From that, we'll come up with a guess of what we think angular position as a function of time can be expressed as, and then from that, we'll see if we can determine what the period of oscillation must be. So let's pick up where we left off. We can replace alpha with d omega dt. But then again, we can replace d omega dt with d2 alpha dt squared. Okay? So now we have the second derivative. Oh, d2 alpha. I'm losing my mind. d2 theta, of course, right? Forgive me. d2 theta dt squared is equal to negative mgr over I times sine theta. Now here's where things get interesting. This is a differential equation. It says, are there any functions for which I can take the second derivative, and it gives me the sine of that function. I don't know any solutions for that. However, I want to invoke something known as the small angle approximation. Try something on your calculators. Seriously, grab a calculator if you have one nearby. I want you to try something for me. First of all, make sure you're operating in radians mode, not degrees mode, for all your trigonometric calculations on your calculator. Can you do that? Set it into radians mode. And try something for me. What's the sine of 0 radians? So we're going to make a quick data table here of sine of theta versus theta itself, and we'll start with 0. Yeah, sine of 0 gives 0. Okay. What about sine of 0.01 radians? Oh, I've got this backwards. Sure. Okay, so when theta is 0, sine of theta is 0. When theta is 0.01 radians, what's sine of theta? Pretty much 0.1. How about 0.05? What do you get? Yeah, about 0.05. How about this? Take the sine of 0.1 radians. What do you get? You get about 0.1. This is interesting. Now, what do you consider to be a small angle? Let's look at the unit circle and get a reminder of what a radian is. Now, I can relate to angles pretty well. I know that that's 90 degrees, and that would be 45 degrees. I know if I go all the way around, then that's 360 degrees, also known as 2 pi radians. I'd rather call that 6.28 radians. So I guess over here is just a little more than 3 radians. That would be 3.14. So 90 degrees corresponds to about a little less than 1.6 radians. So 1 radian is somewhere around here. In fact, 1 radian is about 57 degrees. So that's not a very small angle. That's even greater than 45 degrees. So what would be a small angle? Maybe 10 degrees is a small angle? How many radians is 10 degrees? Well, there are pi radians for every 180 degrees. So if you take 10 and divide it by 180, and then multiply that times pi, you get something like 0.17. So I don't know, let's go up to 0.2. Even that's maybe a little more than 10 degrees, but certainly less than 20 degrees. And if your calculator is indeed set to radians mode, when you take sine of 0.2 radians, your calculator gives you, if you round up to 2 sig figs, 0.2. I think maybe your calculator says 0.1987 or something like this. So as long as the angle is small, as long as we're willing to deal with angles that are less than 20 degrees or so, then the sine of theta is pretty much the same thing as theta. Well, that's huge. That allows us to make a substitution here. I can replace sine of theta with theta itself. So now we get to step 7, and we have a differential equation that says the second derivative of the angular position with respect to time is negative mgr over I, which is all some constant multiplied by theta. See, is this starting to look familiar? I need to think of theta expressed as some function of time so that when I take not the first but the second derivative of that function, I get a negative constant times that very expression for the function that I'm taking the derivative of in the first place. And you know how this goes. You could try to guess that theta equals e to the ct, but that's not going to cut it. Well, there's all sorts of guesses, but you know what this is going to be. Theta is probably theta maximum times what? Cosine omega t. Well, let's see if taking the second derivative of that expression gives us a negative constant times this expression itself. So let's take the first derivative. D theta dt is equal to negative omega theta max sine omega t. If I take the second derivative I get negative omega squared theta max cosine omega t, and then we see all of this theta max cosine omega t, well, that just is theta itself. So we've done it. Step 7 of the work that we got to, just based on applying Newton's laws and our understanding of torque, it matches the expression we get based off of a guess, provided negative omega squared is the same thing as negative mgr over I. Negative omega squared is negative mgr divided by I. Now I'm going to cancel out the negative signs and take the square root. So the angular frequency for a physical pendulum is equal to the square root of mgr divided by I. And frequency in hertz is angular frequency in radians per second divided by 2 pi radians per cycle. So the frequency in hertz is 1 over 2 pi times the square root of mgr over I. So that means the period, being the inverse of frequency, the period must be equal to 2 pi times the square root of I over mgr. This is all starting to look a little too familiar, huh? The period for a mass spring system is 2 pi times the square root of m over k. The period of orbit for a satellite is 2 pi times the square root of r cubed over gm. The period for a physical pendulum is equal to 2 pi times the square root of the rotational inertia divided by mg times the lever arm. Is this always the case? Is the period for any sort of oscillatory behavior, for anything that undergoes periodic motion, is the period always 2 pi times the square root of some fraction? Seems to be the case. We'll find at least one, if not two more examples before this unit of study is over that verifies that guess. Now, in any case, two of these three represent simple harmonic motion, and one of them is just periodic. Do you know which is which? Right. The mass spring is simple harmonic motion. The physical pendulum is simple harmonic motion, whereas a satellite, we can only call that periodic motion. Simple harmonic motion is a subset of the study of periodic motion. This small angle approximation, that was a key step in our derivation. One thing you can look at, remind yourself of something you probably covered a few semesters back in your math class. You learned about series, and you can do Taylor series or Maclaurin series. So do you remember what the series expression is, the series expansion is for sine of theta? If you know what the series expansion is for sine theta, you might be able to relate better to the small angle approximation. I'll provide a video lesson on that if you're interested in watching, that you can watch following this one. So for now, thanks for tuning in, and we'll move on to other examples of simple harmonic motion in the remaining video lessons for this unit.